Welcome to the final session in the Foundations of Computer Network series. And in this session, we want to have a look at a few technologies to wrap up the module. So let's get into things. First on the list is wireless LANs. And remember, there are two standards. We have the 802.3 standard, which talks about wired LANs. And we have the 802.11 standard, which talks about wireless LANs. Remember, in terms of wireless, we are not using cables to communicate. We are using radio waves. And the advantages, therefore, are one, mobility, in that we are able to move around with the devices and still be connected to the networks. And also in terms of implementation cost, it might be a little bit more cost effective because we have less components that we're going to deal with in terms of wires, etc. The disadvantage is going to be speed and also security, given the fact that anybody can now hop onto the network if it's not secured properly and be able to get access. The other thing that becomes important here is just a reminder of something that we would have covered previously, DHCP, Dynamic Host Configuration Protocol, which allows you as network professionals to configure a range of IP addresses which are to be used on the LAN, so that when a device connects wirelessly, it will automatically obtain an IP address. The other thing that is on the agenda is an understanding of CSMA-CD and CSMA-CA. And please note that the one that says CD works with the wired technology, whereas the one that deals with CA operates on the wireless technology. So CS means carrier sense, MA is multiple access, and therefore CD means collision detection, whereas CA means collision avoidance. So I guess the question here is, what is a collision? And a collision is when two or more devices are trying to communicate at the same time over the medium. And because of this, the signals are going to collide, and then they are going to become corrupt. And once they become corrupt, then what it means is that we need to retransmit the packets which would have been transmitted so that the communication can take place properly. So on the wired networks, we operate using collision detection, meaning the devices are going to look to see whether or not a collision has occurred. And if the collision has occurred, then the devices are going to resubmit the packets that they had transmitted prior. The challenge, though, is if both devices attempt to resend at the same time, then we are going to have a collision again. So what happens is that each device will activate a random timer. And so a random amount of time will be issued to each device that will indicate when they are going to try to resend on the network. And the hope here is that because of this randomization, when they attempt to transmit over the medium, then at that point there will be no collision because they will be the only device that would be transmitting. So that's how collision detection operates. In terms of collision avoidance, the devices are going to look on the medium first to ensure that the medium is free. And if it is free, then a jamming signal is going to be issued by the device that wants to transmit. And the purpose of this jamming signal is to indicate to the other devices that data is about to be sent on the network, so that if they had intended to send data, they would wait until the jamming signal has been removed from the medium. So that is collision avoidance. Now there are some components that are essential in terms of building out the wireless LAN. I would just want to quickly cover some of the concepts here. So let's start out with BSA, the basic service area. And this is just the physical area that is covered by the by the access point. Now, please bear in mind that the access point is going to have a range. If the device goes outside of that range, then it's disconnected. If it falls within the range, then it's connected. We can also have a set of access points that are working in harmony with each other. And once we have this, then what we have is a basic service set, or a BSS. We can also tie these access points together by a distribution system. And once this is done, then what we end up with is known as an extended service set. And for all intents and purposes, all of the access points which are tied together by the distribution system are going to be viewed as being a single access point. In other words, all the access points are going to have the same name, and when we move from one access point to the other, as a user, it's going to be transparent to us. It is going to seem as if we are actually connected to the same access point, even though physically we have moved on to another access point. If we do not have a distribution system, in so much so that the devices are acting independently of each other, meaning they would have different names, they are not tied together, then once we move from one access point to the next, then we will realize that there is a change in the name of the access point, and in this case it is known as an independent basic service set. Two other things that we need to cover quickly. One, we need to understand what's a collision domain, and two, we need to understand what's a broadcast domain. Let me start with the broadcast domain first, because this is something that we have spoken about before. So in a broadcast domain, what we are saying is that when we send a packet to a particular address, then it is sent to all the devices which exist on that in that domain, or in that network segment. So what we have here is that hubs and switches have one broadcast domain, and you would know by experience that a switch has one broadcast domain, because when we are talking about subnetting, one of the things that we ensure that we identify is the broadcast address for that network segment. Please bear in mind though that routers have different broadcast domains for each interface. And remember, when we talk about an interface, we're talking about a connection point, or a port that is affixed to a NIC. So that covers broadcast domain. Let's now have a look at collision domain. So we spoke about collisions earlier, and we are saying that when two or more devices are trying to communicate on the same medium, then it is possible that the packets, well, at the same time, then it's possible that the packets are going to collide. And that happens because they are on the same collision domain. So if we look at a hub, for example, a hub has one collision domain. And this tends to be very bad, because what it means is that as we send the packets, there is the possibility that these packets can collide, by virtue of the fact that all the devices are on one collision domain. With switches and routers, however, we find that we now end up with multiple collision domains for each interface. So put it this way: one collision domain is bad. Multiple collision domains is better, because what it means is that it reduces or makes the possibility of collisions next to impossible. So if we look at the diagram here, we have we have a switch that has 24 ports, and what we end up here with is 24 different collision domains, which is good. Now quickly talking about circuit switching and packet switching. So when we are communicating over the network, we are using something known as packet switching. We have spoken about this before. We have some data that we want to send. This data is divided into chunks. These chunks are then sent across the network. in an arbitrary order, and then they have to be reconstructed on the receiver, so the sequence number becomes important, and so on. This is what we call a connectionless protocol, simply because the connections which we are setting up can be different. That's number one. So each of the packets can travel a different route to reach the receiver. And also, we need to ensure that we know the order in which they have been sent, or the order in which the packets have been sent, so that we can reconstruct on the receiving device. For circuit switching, however, things used to operate differently, and this is the kind of protocol that was used in the telephone system. So there are some electronic devices which are known as switches, which establishes a communication path between the caller and the receiver. The challenge was that these electronic devices obviously are going to be finite, so it is fixed in number. And once a path has been established between them, then it means that path remains intact for the duration of the phone call. Because of the fact that they are finite, then it is very possible to end up in a case where someone is trying to make a call but cannot make the call because there are no pathways which are available, because all of the available switches are being used and are being connected to facilitate communication for different persons who have already initiated calls. So this was the how things used to operate. We are now seeing, therefore, that packet switching is going to be a better option in terms of transmitting data, and that is what is being used in terms of the network. Just to indicate, though, that there are some switching techniques that we want to bear in mind as well, with the predominant one here being the time division switching, and a feature known as multiplexing is actually used to ensure that this operates. So what is multiplexing? It is whereby we are sending several signals over the same media or medium at the same time. And there are two predominant ways to achieve this. One, we can divide up the medium into separate channels so that we can send signals or data in parallel. Or we can use the entire capacity of the medium at an instant in time, but then we separate the data that is being transmitted via time intervals, meaning at time interval 1, device 1 would send, at time interval 2, device 2 would send, and so on. And this would happen in a round robin fashion. So once all devices have sent a piece of data, then we go back to the beginning of the line and we continue again, so that they can now send the second piece of data, and this continues until all the data has been sent. So with time division, what we are saying is that the entire capacity of the medium is being used to transmit for a device at a particular instant in time. Whereas in frequency division, what we are saying is that we are dividing the capacity into different channels, and we are allowing multiple devices to transmit on these different channels in parallel or at the same time. This chart now kind of shows the evolution of mobile networks, so from 1G up to 5G, just to indicate that in earlier versions we had things like SMS and MMS, where SMS is short messages which are being sent, text messages, and MMS is where we're sending multimedia messages, so we can send not only audio but pictures. We can also send video up to a particular length. Now we're moving into 5G networks, which are faster, have more capacity, and because of this, we're talking about IoT devices which are able to connect seamlessly to these kind of networks. And so there are slew of applications which are coming down the line. For example, smart healthcare, because of the low latency and the kind of speed that we can get, it is theoretically possible to do, example, surgery remotely by having different experts who are able to see what is happening, communicate, share expertise, etc. So there are a wave of things that are coming in the future based on how the technology matures. Now moving into cloud computing architecture. And whenever we talk about cloud computing, we're talking about the fact that we have compute resources which are being stored remotely and accessed remotely. So there are two things that we need to understand here, or two concepts. We have on-premises and we have off-premises. When we talk about on-premises, we're talking about the fact that the computing resources are local to the organization, so they are physically there at the organization. And when we talk about off-prem, we're talking about the cloud, so they are remote. What are some of the computing resources that are important to us? Well, there's storage. We must be able to store data. Then there's processing speed, so we're talking about CPUs, and we want to have as much CPU power as is possible. And then there's also RAM. We want to have as much RAM as possible. So these are some of the computing resources that we are talking about when we talk about cloud services and what they offer. Now, just to note that there is also the concept of virtualization. And there's really two concepts here. We have virtualization and we have containerization. So the diagram here, I think, clearly explains the differences between the two. Note, in virtualization, we have a host operating system. But on top of that, we can create different segments. And inside of these different segments, we have a guest operating system or a different operating system that is running if we so choose. So for example, we are on a Windows machine. Let's say it is Windows 11. And we are creating a virtual machine that uses a Linux OS. And we are also creating a Windows another machine, a virtual machine that uses maybe Windows 95 for whatever reason. So what we now have are two guest OS, one being Linux, one being Windows 95. And these containers or virtual box are being monitored by a hypervisor. And the purpose of the hypervisor is to ensure that the data between each of these virtualized systems are kept separately. So the resources are kept separately. The RAM is allocated differently to each of these different partitions so that there's no, for want of a better word, cross-contamination. And the tools that we have at our disposal here are VMware VirtualBox, for example. In terms of containerization, please note that we have one operating system, and what we are saying is that each of these segments or partitions are sharing this host operating system. So it is the container engine that will actually separate or distinguish between each of these partitions so that this cross-contamination that was mentioned earlier will not take place. Now, containerization is normally used by developers, and one of the benefits that they get by doing this is that different versions of applications sometimes tend not to work with each other. And we're talking about libraries. So if you look at the image here, you realize that we have an application 1, application 2, application 3. But the libraries that they utilize can be different. So for example, app 1 might be using version 3 of a library, whereas app 2, which is the same app doing the same thing, is using version 5. And what we can do then is keep these applications separately, bundle the libraries that they need or the dependencies, that's the terminology, bundle what they need together, and then keep them in separate places so that they can still execute, even though the technology might have matured far beyond what has been deployed. And the two tools that you'll find being used often in this regard is Docker and Kubernetes. Moving on, and we're still talking about cloud services here, just to indicate that we have on-premise and all of these over here are off-premise. We mentioned that before. But just look at on-premise. What are you going to manage? You are managing all of this. So once your organization have servers on-premise that is being managed, then you are in charge of storage. You are in charge of setting up the servers. You are in charge of doing the networking and ensuring that things are able to communicate with each other. You are also responsible for setting up the operating system, doing any patches that are necessary. You're responsible for setting up middleware and all of those stuff. Now, if we're looking though at the off-prem, then there are three services which are available. One being infrastructure as a service, one being platform as a service, and the other one being software as a service. And as you can see in orange, the orange indicate what the cloud service provider would be managing, and the blue represents what you would be managing. So on platform as a service, you are responsible for installing the applications that you're going to use, and you're also responsible for the data. The cloud service provider would be responsible for installing the operating system, setting up the servers based on your requirements, of course, ensuring that the networking is done, things like that. Which means if there's a security patch that needs to be run, then at the platform as a service, it would be the cloud service provider who would install the patches. But if it was infrastructure as a service, then you would be responsible for installing those patches to the operating system. And finally, we're looking at the network topologies, and the three that we're focusing on are the bus, the ring, and the star. We have been using switches, so the switch configuration is what is represented here by the star, where we have the switch as the connecting device and all the other devices are being connected to that. Traditionally though, we used to have what is known as a bus architecture, which is a shared medium, and all of these devices are connected to the shared medium. And remember, we spoke about collision domain, so what this implies is that this is one collision domain. So if two devices attempt to speak at the same time, then there's going to be a collision on the network. And we spoke about how we handle that already. The token ring is almost like a bus. So it is, think of it as being a bus that has been wrapped around so that it connects to itself. The difference though is that in terms of communication, there is a token that is passed around the ring. And each device that has the token can transmit. In other words, if you don't have a token, you cannot transmit. So think of this as being where we said that there's going to be that jamming signal. So pretend that the device that has the token would now issue a jamming signal telling the others that they can't communicate or they can't transmit at this time. And only the one that has the token is able to transmit. And that's it for us, folks. We have covered all the essentials that we should cover. So take care.